So we get a couple more topics done this afternoon. These are hopefully not real stressful. The first one is NTP, the Network Time Protocol. It runs on port 123. Pretty simple to remember there for the port number. This is one I just stuck in here that is considered the oldest or one of the oldest internet protocols. Was in operation prior to 1985, still in use today. So it's nothing that is brand new, but it also is something that just works. And the question is, why do we go to all this trouble? Why do we really care so much about time? And all you security guys know why we care about time. To track security breaches, network usage, problems affecting a large number of components can be nearly impossible if the timestamps or the logs are inaccurate. It is important that all of the devices have the same time. It's useful, helpful if they all have the correct time. And it's not that difficult to get the correct time because there's a lot of public time servers that are available that we can synchronize our devices with. Our Windows machines get synchronized. Microsoft has a time server, and if you look at the traffic, the multitude of traffic that runs on a Windows machine, a time server is one of those things that's available to you. It's an important in a Active Directory domain. Active Directory domain, if the workstations are more than 5 minutes out of time with the domain controller, the controlling server, you can't log in. The system, when you install Active Directory, the management with Kerberos and all the other bells on it, when you install it, it installs its own time server. We can configure our own time servers, but why do we want to have them? What happened? Did one thing cause the other? What happened first? Did one event, and we always call them cascading casualties, did one event cause another event to happen at these things? So we want to know when it happened, what order they happened in, and if we have a whole bunch of different logging coming in using syslog coming into a single syslog server from multiple locations, did one event cause the other one? Or how did one event or one action or one configuration impact on the other? And that's the other thing that we would look at, is the modification times. To review, and this says in shared file systems, I'll go back to Active Directory because I did Active Directory for a long time and we used Active Directory in the network. If we have a large organization with administrators in multiple locations and each of them makes a change, which change becomes effective? And that's going to be based upon the time. And it needs to be based upon the correct time to do these things. Otherwise, synchronization gets really confused with Windows if we don't do those things. But in the shared file systems, which change gets to be the real change, the save change, the accurate change? NetWare used to actually allow two users to be editing a file at the same time, and if you think that couldn't cause some issues, they're editing the same sentence at the same time. Which one of them gets saved? Well, the one with the later timestamp on it's going to get saved. Same with the Windows with the saved with the shared file systems, the shared files. And in Windows, only one person can have it open at a time, but I updated and then you updated 3 minutes later. Yours is the one that's going to be saved based upon the timestamp that would be on the device itself. Billing services. How long did somebody use something? And we've kind of talked about that. IT doesn't go build 1,000 widgets to make the company $10 million. IT doesn't build anything. IT makes the building of the 10 million widgets more efficient, and that's where the billing services comes in. Who uses the services? How much do they use the services? If it's not a fixed line for the budget, sometimes the billing is based upon usage, that manufacturing used a certain service for a certain amount of time, and here's the billing rate that we're going to do. We're going to bill the services and charge the the individuals that are using the service in order to support the IT department. Similar applications with billing services, who used what, when, or, when did somebody log on? When was the first attempt to compromise the passwords? What happened after that for the things? And some things are by law. There's a lot of policies that apply to IT. Two of them are here, Sarbanes-Oxley and HIPAA rules. HIPAA rules, HIPAA security rules, these guys require accurate timestamps on one of the things, and there are lots of one of the things that I have, but if you get into a situation that you're working for a company that gets involved in a lawsuit, you got to maintain all this stuff. What was the timestamp on the email? Back to the who knew what when. What are the timestamps? Are the timestamps accurate? And they do need to be accurate for all of the things that you can think of that we need these things to happen. This is introducing NTP. This is if we don't have NTP on these things. So we have a situation here that the servers are without NTP. This one's 902, 903, 901. Not really all that accurate. With NTP, they're all going to have the same time. And that's what we want. Everything to have the same time. And hopefully going to have the correct. Again, there are lots of time servers available, local or public time servers, and you can go and Google can help you out here if you want to do that. When we first put in Active Directory, we, I guess, didn't understand the Microsoft time server, but we couldn't do what we thought we needed to do with it. So we went out to the internet and just got a time server, a little piece of software called Time Server, and it was free. And it allowed us to pick our master, and we picked a master for university that was close to us. Which was just a few miles away, and then they would go to someplace else. We'll look at some of this infrastructure that goes on here in a couple minutes, but eventually we want to get back to the master clocks, to the nuclear clocks, the GPS clocks that are available that are not connected. NTP, the NTP server, it's an internet protocol, synchronizes clock times on devices in a network by exchanging time signals. It works at the application layer of the TCP/IP OSI model. So we've got to have this thing, and it uses, by default, uses UTC, Universal Time, Zulu time for all of you who have used Zulu time. Greenwich Mean, Universal Coordinated Time, or Coordinated Universal Time. Universal Time Coordinated, UTC. Sends periodic requests. The NTP, the clients, we're going to have client-server relationship again here. Sends periodic time requests to the servers to obtain the server timestamp, and then it's going to adjust the client's clocks. The clients are going to adjust their clocks so that they come into time, into synchronization, have the same time as the time servers that we have. If we're too far out of time, the client may ignore. Important to the network, timestamps on log messages, what happened when we do these things. User authentication. When did a user authenticate to the network? Yeah, they authenticated at this time, so maybe they did do this. When were changes made in the logs? Who made the changes? When was the change made? Those kinds of issues are important on time. Synchronize the time in all the clients to milliseconds. So it's going to be a moderately accurate milliseconds. Pretty good look at what goes on here. The NTP servers can be configured for authentication. Why do we want to do that? Because we want to be sure that our devices are getting the time from our time servers to do these things. Can be configured to authenticate for the NTP time synchronization. The authentication mechanism uses authentication keys, and the configuration's down here, and I think that one of the labs is to do this. The authentication keys that a server provides are defined by entering the NTP NTP authentication key command. We have a number here and an MD5 value. And then the command to initiate the time source at the client, the NTP trusted key, and then the key number. NTP authentication key, we created the keys over here and a value that went along with it. The client permits the time synchronization only after checking the authentication that the authentication keys are valid. If authentication fails, it's not going to accept the time from the time server, from that particular time server. So again, we want to be sure that our devices are the ones that are updating our servers. Clients, the Cisco devices, can be clients and can be servers. They can be configured as both for these things. The clients are the devices that receive the updates from the NTP servers, and then the NTP server, this is the configuration. While we got that one up, a real simple topology here. This is the NTP server, and it is already configured, and I set its time. I have to set the time each time because they don't keep up once I turn them off. To see what the time is on the device, use the show clock command. It says it's 1541. It's close. 1541, 1377. Since it's the master and I don't have some place for it to get updates, I've got to do a manual configuration of its time. Central Standard Time, Tuesday the 23rd of June, June 23rd, 2020, and I think that's where we are right now. If I go in here and do show run, in order to make this thing a master, we just go into config and make it a master, NTP master. We could make it a master and a client. Packet tracer, obviously, so I don't have any place for it to go get its time from. We could make this the master for our network and make it a client for the internet, to where it went to an external time server that's going to be updated from one of the accurate clocks, so that we now have accurate time on our network to do these things. An accurate time. So this one was pretty close on the clock. These may or may not be, because I changed the master's time. And and I didn't do a show. I usually do a show here to see what's going on with these things, but I didn't in this case. Let's do a show clock. And yeah, this one, 2142, this one's universal time. This is UTC. We're in -6. If we wanted to change this, we could go into config T and do clock time zone, and then it says the word here, and I'm in Central Standard Time, and I think we're -6 for the changes here. Do show clock, and now I am showing the local time and not the universal time, but that's something that does have to be configured. When we look at what we can do, we can show NTP associations, and that shows us 192.168.5.1 here. This address is the NTP server. The delay, the offset, if it were the offset, is the error that we have, and we don't have any real error here. The tilde here and the star says that we are here. We say that we're configured, and the star, the system peer, the star means that we are actually synchronizing. Let me go see if I can mess the other one up. Okay, so NTP, we did associations. Show NTP status here. For the clock, it says unsynchronized, stratum 16, no reference clock, even though we are in time, and it says that we're set up with a server here. The numbers in here, the frequency, the precision, the reference clock tells us that the reference time is 000 Monday, January the 1st, 1990. If we initially install this thing, I think that's the time that you're going to get. Stratum 16, and keep remembering where we are. We're going to talk about stratum here in a couple of minutes. We'll show you a graph or an image of what stratum looks like. What a stratum is. Basically, it's how far you are away from the time server. Status. This one says its clock is synchronized. And this reference is 192.168.5.1. That it is up and running, getting its time from the one that we set up as the NTP master. And this one's universal coordinated time also. And to show the NTP associations, we get the same look here, that the address 192.168.5.1, and as we go on down, which says that we are connected to it, and we don't have a lot of offset here, so we're in reasonably good shape with it. If I bring up another device, and I can put it in here real quick, and let's go in here to our cheat gig 00. We'll turn it on, and this was the 5, right? 192.168.5. We'll call it think that. I don't remember what all the other ones are. If I now want to go into this thing and do a show clock, then this says that we are March the 1st, 1993. And FigT will do NTP, and we have the authenticate, the master, the server, and NTP, our server 192.168.5.5.1. And that's all we have to do to configure an NTP server. This one's going to take a while. Associations, it says that it's going there. We have an offset, show NTP status. What I want to show here, up on synchronized reference, for Stratum 16, no reference clock. It's unsynchronized. We haven't got to the synchronization yet. When we get there, the drift 4 is a really big number here, which I don't have with the should be, I think, in the offset associations. Yeah, here's what I was looking for. The offset. This is how far we're out of time with the time server. So it's going to realistically, a little bit at a time, I think that packet tracer eventually just jumps from one to the other when it decides that it's time to do that. But it should incrementally bring the device towards the time server time. I'll let this one run a little while and come back to it a little bit later, probably after we do DNS, and see if it actually has gotten it into time. But NTP server, NTP master, two things that we can configure. And back to the one that's a master, we can configure it with a server address too, to go to someplace else in order to do these things. The show NTP status displays the current status of the time synchronization. It can act as peers and provide synchronization to other devices, so we can synchronize from one device to the other. IP address are statically configured on the peer devices to enable communication and maintain accurate time. The show NTP associations displays the other devices to which a particular device is associated as a peer, the things that we saw. And this is what is a stratum, because one of the things that we saw, one of the word sets, I guess, in here that we saw when we do, what was the status, I think. NTP status. It says that it is, well, we're doing good here. Clock is now synchronized. We're at stratum 9. And sure enough, we're up to where we should be. So it went from 1993 to 2020 relatively quickly, 2149. Still universal UTC time, universal coordinated time to get from one to the other. It says it's stratum 9. And the stratum here, what is a stratum level? It's basically, or not basically, it's how far away are you from a master clock. And this one, the time master, I've set a stratum level on it. So the stratum level, large companies got to have lots of devices, maybe a lot of devices acting as the time servers. Which time sources are likely to be the most accurate? And those are the ones that are going to be with the lower stratum level. Is a measure of the synchronization distance from the primary. Stratum 0 devices, atomic clocks, GPS clocks, They're going to be the most accurate of them. Can't be connected to the internet. So one of the keys, and I guess one of the maybe many things to make a note of, is the Stratum 0 devices cannot be connected via a network connection. Uses a reference clock for the Stratum 1 time servers. The Stratum 1s are on the network, so they're going to be network connected. The Stratum 1 devices are a Stratum 1 time server, and then we're just going to go on down the line. Stratum 1 to Stratum 2 to Stratum 3, on and on and on. The Stratum 1 devices are the most accurate, accessible via the network, normally synchronized via the Stratum 0 reference clock. Stratum 2 are synchronized to Stratum 1, Stratum 3 to Stratum 2, on down the line. So what it looks like is this. We have the authoritative clock, which is connected to, not via the network or the internet, but is connected to the Stratum 0 to the Stratum 1 devices, which are going to be the most accurate server, or the most accurate time pieces that we can connect to via the internet. And then 1 to 2 to 3 on down the line. The Stratum, how far are you away from the time source, from the accurate time source we have? So we have a couple of labs here that I want to wait on and then consolidate and end the day on labs, unless you're really to do that. When we do that, and the next grouping here is going to be DNS. Let's look at DNS, domain name service, domain name system, for a few minutes. DNS is that service that allows us to type names instead of IP addresses when we're trying to go someplace. www.cisco.com, learning.leaderquestonline.net, whatever we want to do, and we get the lookups. We've looked at, and we're going to talk about the process here in a minute. I want to get this one done before I forget to do it or get this one shown. We've looked at this before. These are the quote 13 unquote name servers that are available in the world. Well, there are a whole bunch of them, and we looked at this when we talked about the Anycast addresses, because we have a whole bunch of them. They all have the same IP address. I want to look at this one at the L, and this was up here in Anchorage, Alaska, 199.7. I guess I could write that down. 199.7.83.42. And then I want to look at the autonomous system number as to how we get from one to the other, 2144, to be able to do the resolutions. Now we got to find another F server. Let's go down here and see, was that an F or an L? Another L server. So let's go to Denver and see if we have an L server, and sure enough we do. 199.7.83.42, autonomous system number 2144. So these things match up. We go to the closest one to us. A lot of times, and all you security folks have heard, hey, if you can just bring down those 13 servers, you can bring down the internet. But this is where those 13 servers are located, all over the world. These are going to be called the root hints when we look at a DNS server. So we have the quote 13 unquote servers, but we have a really big population of them, different locations. You go do the lookup to the one that's closest to you. Sometimes parts of the internet does get slowed down by attacks on DNS, but I don't think that the entire internet's ever been brought down. Theoretically, could it? Yeah, but it would take an awful lot of attacking to go on to do this. DNS, TCP/IP name resolution service that translates the FQDN into an IP address. DNS is one of those services that uses both TCP and UDP. TCP, zone transfer, which is, we'll look at a zone here in a few minutes, and if we want to have a backup server, we BACKUP, a backup server, then we would transfer all of our info info from our read-write server to a read-only server, and this would help in lookups. UDP here is used in lookups. When we go to find the IP address of www.cisco.com, it's going to use UDP. What kind of sort of really happens is the packet size is going to dictate it, but zone transfer is going to use TCP, lookups are going to use UDP. So it's one of those protocols that uses both TCP and UDP. We're going to resolve FQDNs for those things. A domain is a group of computers whose communication is managed as a unit. A domain is a unique name that identifies a domain. A domain could be, leaderquest.net, leaderquest.com, ESAA.com, Microsoft.com. The fully qualified domain name is going to be the www, which represents a resource, represents an IP address. A computer, a website, or a web server, or something like that is going to be represented by that. Host name, the unique name given to the node in the TCP/IP. When we combine the host name with the domain, we get the FQDN, the fully qualified. The domain name, the information about the hierarchy of the domains and the hosts under each domain, which is referred to as the DNS service for mapping domains, and then the FQDN denotes the specific location of the host. Let me go back to this one here. The domain name space, the information about the hierarchy of the domains. I think that while we've done this, look at this real quick. I want to, and let's see if, anyhow, we'll try something different when we get over here. I want to look at a DNS server. So, to do this, anyhow, well, let me log in here. We'll make it work. What I can do, I think here, is to go into my VM, and let's try, I guess view, let's try full screen. Still didn't do it right, did it? But we're close. Let's log into this guy, and I think that I have, and I do have, and I can't make this any bigger, so if you got to squint, you're going to have to squint. Make DNS work. We start with the root, and then we're going to look at these things, and we have the top level domains, the .com, the .edu, info, IO, mil, net, org. I've done some pinging to try to get some records in here. There are a number of records in here. The edu is eCPI, and when we look at this www here, and it doesn't really go to directly to a location. It has a CNAME, a canonical name, which means that it's an alias. It then tells us to refer to this site over here. I'm going to look at a different one to look at that, but .io to get to there. The live-v2 edu eCPI pan the onsite.io. Okay, so we have that. And we have the IO here, pan the on-site. And in here, I guess it has gone away. These do time out. So if I go back and ping that again, and maybe the others won't have timed out, we can look at those things. The one that we use, the www.esaa.com, has got a similar thing. It goes to cloudflare.net. So the alias, or the CNAME, the canonical name, is an alias, an A record or a 4A record, an A record for IPv4 or 4As for IPv6, and I think this one will have it unless it's timed out too. So let's go to the .net down here and go to Cloudflare. And under Cloudflare, I think it was CDN, ESAA, and we're finally getting there, but it is timed out. Let's see if I can get a record back in here then. I guess they all timed out. I thought that I did this close enough. I don't want that one. And let's do a couple others here. And .com. So we have these. Some of these you see are coming up with IPv6 addresses, some of them IPv4 addresses. If the systems can use IPv6, If they have IPv6 running, that's what we're going to have. I have to go up here now and refresh this thing for those to take effect. It says cache lookups. When I go in here, what was it? esaa.com, and that took me to the cloudflare.net. I think it was in the CDN and the .com and under the .com. The ESAA, we now got records in here. So we have a www, IPv6 is 4A. And this is the IPv6 address for this guy. And then the IPv4 record 104.24, 114.59. When we look at a record here, it's got the entire FQDN, the IP address, and down here we have a timeout. And the reason that they did timeout, I thought they were a little longer. This thing is good. It looks like for about 9 minutes. It's good for now for 8 minutes and 59 seconds. The records, this one is 9 minutes. It hadn't started its countdown, I guess. The records are good for a certain amount of time. They do have a TTL. They do timeout. Why we want to do that is we may change things. So DNS needs to be looked up. But this is one of those that went to a CNAME record, a canonical record, an alias. The net, the CCESC, I'll get back into the net. The CCESC.net just goes directly to it. It has an alias here, but it also has an A record for the www. The alias here says that if you just type in CCESC.net, I'm going to take you to www. That's how we get that. We now, and I've got a really bad habit about not typing in the www, the first part of it, just typing in the domain. When we go to the domain, it then gives us the lookup. What happens in the system, and we'll have some images, but let me see if I can drag it out here, draw it here. If we go to the DNS server to get something, if we have we're going to have two types of lookups. We're going to have an iterative lookup, iterative and recursive. Why can't I remember recursive? Recursive just gives us the answer. So the recursive, get back to my pen. The recursive here, if I am me on my computer and I go to my DNS server and ask it for, and in this case, www.ccesc.net, it's going to return to me this IP address. That's going to be a recursive lookup. If it didn't have it, which we had a little while ago for these things, it says, hey, I don't have it, but let me go look for it. This is going to be called an iterative lookup. An iterative lookup. What happens here is we go to the root, which is the start of all this. You can see it here represented by the dot. We go to the root and say, I need an address for www.ccesc.net. It says, I don't know that, but I know the IP address of the .net server. And it sends that to us. We go to the .net server and say, hey, I need this address. I don't know that address, but I know the address of the name server, the DNS server, and that's what NS2 and NS1 are the name servers, and this is hosted at HostMonster. So the name servers, I know the address of the name server that lists the www.ccesc.net. And it sends us that IP address. We go to it, and then it's going to give us the www. Once that happens, the DNS server, our DNS server, sends that IP address to us. We then put it into the IP cache on our, and you can see the IP config cache on your machine, and I'll show you the one on my machine, and it's probably going to go crazy because it can't. But if you go into it and do an IP config, config spelled right, / display DNS, and I missed display DNS is one word. Display DNS, it's going to give me all of the records that this machine has looked up since it got turned on this morning. So a whole bunch of records that go on and on and on. The one-in-one, I got IMAP one-in-one, different things. That's because this IMAP one-in-one, I've got a one-in-one email account, IMAP email protocol that it uses. So my system is going to update itself. The email client has been updating itself, and it has to do a lookup in order to get to the email server. So we have the iterative lookup, the cursive or recursive lookup that allows us to get those resources. When I go in here and look at, and I always get a mess about when I do, I typically get the wrong things here, but I lucked into it this time. We have forwarders, advanced, and then in here somewhere we have the root. So we have these A, B, C, D, E, F, G, H, I, J, K, L. And we had an L server, I think, a little earlier, 7. Anyhow, these are the root hints for the D root servers, the A, B, C, D. The different ones that we might have, the root hints. I think this one, the F server, is the one that we had earlier. We looked at 192.5.5. These get updated from time to time. And this one hasn't been updated in a while. I don't do updates on these virtual machines because I use them so infrequently. When I turn them on, all they want to do is update, and I can't get anything done. But we have those things that are available. A zone would be something like this. And the zone in here, I got the local, and these would be the machines that were in the local, and then me.local.coldiron.local to do these things. So what I can do, if I own it, if it is a read-write copy, I can go in here and create a delete, a new domain. I can do a new domain. If I want to go in here, type the DNS domain name, I can configure what goes on with this thing. I can put in host records. I can make changes to it. That's when I own the domain. The read-write copy is the primary server that we can forward lookup zones, reverse lookup zones. A reverse zone uses the IP address to find a host name. Typically, we use the host name to find an IP address. Reverses the lookup. So DNS, FQDN, saw a couple of those. The IP addresses, A record, A record, CNAME record. We didn't look at an MX. MX is a mail server. An MX is mail exchanger, is a mail server. We looked at a DNS record, a name server record, and an NS record, and looked at the process for these systems to resolve the name to an IP address when we do that. We also have the host file, and I think that we've talked about this earlier, and it shows up again here, but the host file is a mapping of the hosts to the associated IP addresses. This goes back to when there were 4 computers, 5 computers, 10 computers in the world, and you could write down the name of the computer and the IP address of the computer, and we wouldn't have an issue getting to it, keeping it accurate. And then now we have the 4.33 billion IP addresses. We're not going to write all those down to keep track of them. That's why we need DNS. The host file was the precursor to DNS. DNS, a hierarchical lookup, so that it's a little more efficient, a lot more efficient than the host file. One of the uses that I used to see, and I haven't used one in a long time, is malware, nuisanceware, where you buy this or get a free piece of software. What they would do for the sites that you didn't want to go to is they'd put them in the host file. And they'd put them in the host file and send them to a black hole so that they wouldn't open. Black hole being an IP address, a non-existent IP address, or nothing for the IP address. So that, yeah, it got there, it tried to open something, but it couldn't get to the website that it was supposed to go to. The host file goes into the IP cache, the IP config show DNS display DNS, it goes into that file the first thing when the machine's loaded. So if you have something in the host file, it won't go to the DNS process in order to find the IP address. Left over from the original method to associate names and IP address, loaded into the IP config DNS listing at computer startup, and unique names are assigned to IP addresses. They don't have to be fully qualified domain names. We can make shortcuts using the host file to do these things. Provide an easy way to configure and manage remote systems within the network. And one of the things that I think you did earlier was to configure a host file on a static host name to IP addressing mapping on the router once we configure it. This is not something that's going to automatically happen for us. The host table, a little lab here, DNS, some more DNS, and a few more slides on DNS, and then we will get into the just a few minutes. TCP/IP name resolution service translates the FQDN to an IP address, or vice versa. We looked at both of those. We have a reverse lookup as well as a forward lookup zones that we can configure. Domain is a group of computers whose local communication is managed as one unit. I had a domain in there. I could put records in there if I wanted to, because I'm the manager of that particular one. It's my domain. I can put addresses in, I can take addresses out, and I can create a read-only copy someplace else to do those things. Domain name, a unique name that identifies a domain, and a hierarchical databases stored on separate DNS servers. The hierarchical database, the hierarchy that we use, the root, top-level domain, second-level domain or third-level domain, root, top-level domain, second-level domain, to be able to configure them. And we looked at the process that it goes through for the lookup. DNS functions, IP addresses, and related computer names. Maintain and update databases. Use the databases to respond to the DNS client name resolution request. Translate the host name to an IP address. Work together to resolve FQDNs, fully qualified domain names. The DNS servers do. Because we had the top level domain, we had the root, the top level domain, and then the second level, the ISP that we saw, that each of them had an address that we could go get to. The ISP's DNS server is where you get listed for these things. That's the one that's going to list the IP addresses. So all of these things are going to work together. The other thing, we had forwarders and conditional forwarders, that we can forward queries for certain domains to other servers, and that way we don't have to do the listing on our own. Internal networks, the local DNS server resolve host names without using the external DNS servers. The cached lookups are the external servers, the ones that you saw that were already here, the forward lookup zones. And then this one, this is the domain in here. I have a local, the start of authority. I have a host A record that I put in here, and just us, and then a name. Just this was just as a demo. If we want to do a new host, we put a new host in here, and let's put CCNA June. We can name a device, and you notice that it appended the domain coldiron.local. It appended that to the host name, and then we could put in the IP address. 192.168.77.6. We could do a time to live. We could create the associated pointer record for these things. The pointer could not be created, probably because the reference reverse lookup zone cannot be found. And we can create our own, and then I just did, and here is the A record that goes along with it. The name, the domain or the zone, the domain, not the zone, the domain that it's in, and then the A record, the host record. An A record is an IPv4. A 4A record is an IPv6. We've talked about this, and hopefully this, when you see this picture now, seeing what is in a DNS server. Hopefully it makes a little bit of sense. We have the root, pointers to the top level domain name servers, the .coms, the .nets, the .orgs, edu, UK, on and on and on and on and on. And then we have domains under there. We have the top level domains, and we could sometimes these are called different things. So it could be the second level domain. We could have subdomains under those. Eventually, we're going to get to, based on the whole string of text that we're going to use, get to the individual host. Another image here: the top level domains, second level domains, third level domains that we go to. This one's kind of a little backwards, and I don't know who did it, and I probably shouldn't have put it in here, but this should be the root, these should be the top level domains, and these should be the second level domains. I guess I can do my own auditing on that. The recursive, we talked about that, did an ugly scrawl on it. A recursive, we go to the DNS server, my DNS server. If it's got the answer, it gives me the answer. If it's in my cache, I don't even go there. I just look at the cache and get the answer out of my DNS cache. The iterative lookup, we go to the root, to the second level or to the top level domain, into the second level domain in order to get an IP address associated with a name. So this one here, I need an IP address of DevelopTech or DevTech, developtech.com. Go to my DNS server. It doesn't have it. It goes to the root. The root says, I don't know, but here is the address of the .com. Goes to the .com. I don't know. Here's the address of the DevelopTech DNS server. So we go to it. Yes, I have it. And it gives me my server, the IP address of that FQDN. It then gets put into the cache lookups in the DNS server, and as you saw, the cache lookups do time out. There is a time records. When it goes into our local cache, there's no TTL on those. They stay there until we can flush it with ipconfig/flush DNS, or when we restart the machine, turn the machine off, turn the machine back on, restart the machine, it'll get flushed. Another look at OmniSecure. We're going to omnisecure.com. We go to the DNS server. It doesn't have it. Goes to the root, to the root, to the DNS, to the .com DNS server. From there to the OmniSecure DNS server until it gets the record, and then eventually we get the recursive query. Recursive when we get the answer. And then we are into a number of labs that are available here.